Hello and welcome to week 6. To the specifically to the Max tutorial for week 6. So let's have a look at the plan here and see where we're up to. At this stage you guys should be situated almost midway through your double diamond design flow, building your week 7 submission, which is due this Friday. And not wanting to take you away from that focus, in our parallel online lecture series, which is introducing you to the Max development language that we'll be working in. This class is the random generators and noise one. So let's get going. If we go to modules, down to week 6, you'll see your Max tutorials there. Just click on that and download this file, which you'll see is a Max patch. It's not in any embedded folder or anything because it's just a simple patch that doesn't have any dependent media. And then open Max. And open that example, and you should have something that looks like this. It says randomization and noise examples, exploring random, stochastic, noise, and particle systems. Well, I took that out actually, because we looked at particles last week. So, what are these things? These are examples today of really basic agents, software agents. These are things that will create random outcomes. Things like flipping a coin, throwing a dice. Imagine if software could do that. And how would it do that? How would you make that program in Max to make a randomized dice result? And these are very useful things to have, and they form the backbone of a lot of computing, especially game design is full of random computer agents. And there's lots of different ways of doing that. You might not have really thought much about randomization in general. And so this lecture is going to open your eyes and ears to what this field is all about, and also question it in a way that might be a bit thought-provoking for you as well. So let's begin. So the first example I'd like to look at is a digital coin toss. So throwing a coin, heads and tails, there's only 2 outcomes there. So it's pretty simple. And you can see here that we have a little patch. It's got a few things in it. There's, at the heart of it, an object called decide, which chooses randomly between 1 and 0. And if we turn this on over here and watch very carefully this output down here. So I've got another program over here which is counting how many heads and how many tails, or effectively in digital computational methods, we have a tail as a 0 and a head as a 1. So a digital coin toss is going to give us these values. Now, hopefully, if we add all of these together and then divide, pack a small string together and compare them, if we have an absolute equal number of heads or tails, then we should end up with a value here that is exactly 1. So this is a little bit of computational work that I've put together to test how random is this decide object. Because there's other lecturers at Swinburne that have told me that computing is only pseudo-random, which is really interesting. This is a theoretical branch of computing, of course. And you know, so I'll be trying to test these things out as we go along as well. So here we've got our little metro object. If you've forgotten what that does, I'm just going to break that link there and put a button here to show you that it just outputs. And I might just remove that seed value integer at the moment. It's more about that later. But if I connect this up to the metro here, I can change the timing of which this goes out. So if I put 1000 in there, I can make this send out a little trigger pulse every second. So let's connect that up, and we'll see here when it's running into a toggle. So if there's a head, it will output a cross. If there's a tail, it will output a 0. And you can see here that as we start accumulating our values, we can see that sometimes it drops below 1, sometimes it goes above 1. Let's speed this process up now. So I'm just going to click in here and scroll, click and drag my mouse down, drag that value down, and I'm going to increase the value here. But maybe I'll just type in 5 or something, but don't type in 0. And you'll see I'm really speeding up the process. And the more of these things I accumulate and feed, which is, you know, in a way a really simplistic kind of idea of training, this value will slowly approach 1. It will either be just below or just above. Or I can turn this off. And any time I need to get some kind of flip between a 0 and 1, I can just put a little trigger in here and click. So don't want to say too much more about it. And the reason for that is I read this really cool paper about teaching students how to make stone tools, and the students that made the best stone tools didn't get the PowerPoint presentation. They just got someone not talking to them, chipping away with a flint and making tools, and they were encouraged to pick up the flints and make them. So sometimes just looking and exploring and doing is so much better than me explaining it all. But you can play around with that one. There's not too much more to say about it. It's a digital coin toss. So say we want something that's a little bit more like a dice. And let's just have a look at this example first. I'll just kill that one. And say I want to... actually, let's put that back. If I wanted to make a dice that would, 6-sided dice, I would put random, and I would put its range, I think it would be 5, and I would put +1. Sounds pretty crazy doing that, but I think this will give me a value of 0 coming out. And if I add 1 to it, then I'll get something like a dice. And every time I want to, and you can see there, the first roll that I had was a 0. And then if I click on this again, oh, we've got another one. But you can see here, it will, am I getting a 6? Surely I've got to get a 6. Maybe I will have to put 6 in here. Surely not. If it outputs a 0, and it outputs a 5. Okay, well, I'll have to do some research on that. Let's quickly open up the help file on it, which was Shift-Command-H for help. And it will output a random number with a range between 0 and 1 less than the argument specified. So there you go. That's something that I didn't read, but interesting. So there you go. I can create a random dice there, and the outputs here will be 1 to 6. Over here, I've got another example, and I'm using this really cool object. If you're wondering what this is, just click and select it and get Shift-Command-H. We'll bring up the help file and it will introduce you to this. It's a controller and also a visual display object called multi-slider. And what I've done is I've just pinched one of these examples. There's so many different ways you can set up a multi-slider. And if you look here, all of these the same object. The green one, the pink one, the yellow and purple, they're all the same object, and this one is too. So all I've done is open this tutorial, grab that, and bring it in here, and I've changed one little thing on it to make it look, to fill in, instead of having points, to make it fill in like a histogram. And you might be thinking, some of you might be thinking, oh wow, I can use this object in my patch to create a histogram. Now, this is not a video window. This is a kind of an older object, and you'll have trouble fitting that into Max. But there's other techniques for creating histograms in video. But we're using it today just to show a couple of things here. So I've got a random range of 0 to 127. And it's outputting a real scatter of points there. You can see that there's some low, there's some high. If you can see a repeating pattern in that, then you've got an amazing brain. But I can't really detect anything at this stage. And so this is what we call a random range in computing. But there are lots of other ways to create random processes in computing. So Max also has a step range, this object that's called drunk. And this performs what's known in the maths game as a drunken walk style randomization, where you have a large global range, and yet within that, which is 128, and within that here, we've specified a smaller range where the randomization actually occurs. And you can see it creates this kind of bizarre shape. If we set this range down to 0, then there won't be any deviation at all. And small values, 1 or 2, will not make a huge amount of difference. And of course, you could make it look like that as well. You could say, I want the random range to be anywhere between 0 to 128, and then you would get something that approximates random. But you can do all of these things in between. Which is very cool. So the next example here, I can just turn it on, we'll be outputting that as sound. So I've combined the same kind of patch, but as well as that, I'm using a couple of objects which engage your computer's built-in synthesizer. One that makes a musical note. Oh, just hang on. Sorry about that. I just had a visitor at my door. That's crazy. Okay, so what I've got here is also a little an object over here. If you grab the circle inside, here's a really useful what I call a screen control object. If we double click, Shift Command H, select the object. This object's called a picked slider, which you can look at. It lets you bring in pictures, and or you can also set it up to be a two-dimensional joystick. And you can see here what I've done is I've changed some of these random ranges. So this will set the whole range higher and lower. Sorry, and this will set the size of the range. So if I'm the puppet master of a mad pianist, and I just want them to play around one note, or if I want to play them with all 8 hands, and then I've also set up a timer here to change this every 5 seconds. And you can see there's a really interesting thing that's going on here, using a message box and a line object. Now, this is an interesting technique I call data slewing. So the numbers that are coming out of the random range objects here, they just jump in these really big steps all of a sudden. And if I disconnected this, I could show you what I mean here. So you'll see it jump. Oh, not seeing anything at the moment. I don't know why. Yeah, there you go. It jumped from the straight across there. 26. 72, it's jumped over there. And what I've done is I've set this up to create a ramped line of responses. So the way it works is this object will connect like when you're doing a dot-to-dot picture in a children's book, you're connecting the dots, and that's what this object is doing here. And it's drawing a dot. It's filling in a value every 20 milliseconds. And it's doing it over a time value here of a whole second. So it will slide for an entire second. We could modify this and we could make these 5 seconds. And then it will be it will be continually changing now. And that might be something that you want to use. So what I'm doing here is making more complex agents for my multi-agent system out of simple ones. So if we have a look at the drunk object again, I decided to have a look at monitoring the output. So I've got some other bits of code here. I've got a value here that says add 5 and then set the range in here again. I've put an unusual object in there, more about that later, but that is to set a timing delay before a number is passed back in. That way I can set my volume here, my range here, sorry. And off it goes, and it's climbing. And if I set it in to a size that is beyond 500, let's just watch what happens here. Goes up to the top. Yeah, I have to push it a bit higher for something to happen. But I didn't touch anything then, and this, what it's saying here is if this value goes greater than 580, then subtract 1. Or if the value coming into this object is less than 10, then add 1. And that way I can create some steering forces in my drunk range, and we call this in computing bias. So I don't know if any of you have played lawn bowls, but you go to bowl this ball and it has all this weight on one side of the ball, and off it swings and goes in a kind of a crazy direction out to the side and then swings back in, and that makes the skill of playing a gentle game like the bowls so much more difficult and interesting. So that's what I'm doing there. I'm creating bias in my agent. Jitter has and remember the jitter objects are all ones that deal with video processing, and in particular processing these special signals and max called matrix signals. So here we have an object called jitter noise, which will create a randomized pattern over a 4-plane alpha RGB character 0 to 255 matrix that is 1 by 1 pixel in dimension. And if I send a trigger pulse into that, I will create a random color. Now your color will be different to mine. Don't fret. Every time you click this, you will get a random color. And if you turn that video frame on, you'll get this dazzling, spectacular flood of random colors. And to analyze what's going on here, I've set another duplicate stream out, and I'm using an object called JIT 3M. And M is for, I think it's minimum, that's right, minimum, mean, and maximum values. And what it will do is it will average the screen. And you can use this to test how much red is in the screen, how much blue, and how much, this is alpha RGB. So I've got here all of these values. These are the average or mean values in the frame. So you can see each time I click here, I will get a different set of values, which we could also then test to see, how much red is in a frame or whatever. This could be a way to test an incoming signal of video. Now what I'm going to do is increase the size of my screen from 32 to 32 by 32 pixels. And you'll see we get a checkerboard. And if we make this bigger, and we go to the next noise 2 example, you can see this is a 320 by 240 screen, and we get this what's called a noise pattern, or video equivalent of Gaussian noise or white noise, which means everything is kind of every pixel is randomized without any bias on any color. And noise is a really interesting thing. It permeates all of the cosmos. If you point an antenna into space to try and pick up television signal, you'll get something like this. If you listen to a radio frequency band or whatever, the background radiation of the universe itself creates this pattern. The pattern of billions and billions and billions of reflections and echoes of that original Big Bang. And we have noise from devices, from the core of the Earth, from other astronomical bodies in space that are all part of kind of the signal that we get whenever we put a transducer out in our environment, or some kind of image sensor or microphone to pick up the rest of the world. Other systems that have sensors can also be picking this up too, and it's unwanted in many devices. But today we're creating it artificially, and in that sense we're using an algorithm. And before, when I was introducing to all of these things, they have what's called a seed value in them. And the seed value is in random, drunk. I didn't tell you what it was for in those earlier examples, but it basically creates more complexity and a larger pattern of random. Sorry, a larger set of randomness before something can possibly repeat, and because a lot of the random processes, whether you're looking at a Gaussian generator or a Turing machine or whatever, these computational algorithms that are at the heart of behind all of these max objects, there's an algorithm that creates this random set of numbers. They're not infinite, like the sound of the universe is infinite. And so that's where I'd like to finish today. I've got over here a slider object. And what I'm going to do is turn on these gates, and you're going to see, coming back to the coin toss, we've got these values here. There should be 127. You'll see them jumping around, and you'll see things here. Now what I'm going to do is go up to this little value here. Now at the moment, I'm interpolating 2 video frames at the moment. So what you're seeing out of this window is 2 frames mixed together. And if you look really carefully, you'll see it looks a bit different. It looks a bit more blotchy than that, which is really, really sandy and dusty. Now, you won't see it on the video streaming, but you'll see it on your own computer. And look what happens now if I get this value and I click in there and push my mouse up. And what we're doing now is we're adding 20 frames together. And you can see it looks like some kind of seething grey sauce or something bubbling away on the fry pan or whatever. And occasionally there's some little blotchy things. Now if you increase that up all the way to 500, which is the maximum of this slider algorithm, you'll see that we basically freeze that frame, but there's still an inherent texture in it. And you'll see now that these values have, they're not jumping around as much as these things anymore. They're approximating the halfway point, which is 127.5. And they're getting much closer to that value than these ones that are coming directly off the noise algorithm. And why am I showing you this? Because imagine if we could interpolate more frames, what do you think would happen? Well, in fact, your little jitter window, your computer screen, would go grey after an hour, and it would be a uniform grey. And eventually, you wouldn't be able to tell the difference between any one of those pixels. They would all average out on some grey colour. But what would happen if we let that interpolate for weeks or months? Would it still be grey? Or would it change? It's an interesting thought. And I'm showing you that tonight because I have some work here from another video artist, a chap called Dale Chant, who explored that very question. And here is an image of his supposedly perfectly grey video window after 4 weeks of computing a randomized noise pattern. So this is what you get on a Pentium 2 computer. These are old computers, and this artist Dale Chant, he loved this version of the Pentium because unlike other Pentium computers or other processors, this one showed an inherent bias that formed crystal structures on his video window, which is really, really fascinating. And he's provided me here with a whole lot of different analyses of his window, which he's turned into art. And he's done a false color image here to show you what's really behind that grey pattern, that there's no such thing as random on a computer, that a computer can at best approximate it. It approximates it very well. And it, in the course of a day or a few hours of accumulating a noise pattern, you will not get a crystal. But if you leave your processor and your computer on long enough and keep calculating those interpolated video frames, adding a frame, blending frames, frame upon frame upon frame upon frame, then you'll end up with something like this. So what is it? And how can this be that a computer's random is not random? Dale did a lot of investigation into this, and he believes that these patterns relate to areas on the central processing unit that are hot and cold. And because the chips themselves are not uniform in their heat dissipation, you end up with these intriguing patterns. So he's done a whole lot of these, whole lot of different types of analyses. I won't go into what they all are, but I'll just show them to you. And I'll attach this PowerPoint. So this is just the same thing, but wrapped in a circular arrangement. Sometimes there are things that go strangely wrong as well. And in a computer that has a badly designed CPU. They're all different computers, different types of Pentium. It's Pentium 3. And that concludes our lecture today on random generators and noise. And I hope you found it really fascinating. And start looking for it in computing. See if you can find a few examples for me this week of random computer agents at work. Thanks.